So in the previous video, we derived the relativistic Lagrangian and Hamiltonian, and we looked at how the principle of least action for a relativistic system helps us to arrive at the equations of motion for such a system. So in this video, let's give the relativistic Lagrangian a covariant treatment. So to make a covariant description, it is useful to replace the position x and velocity v by the four vectors. And those four vectors, as we already know, are for position we have x alpha, and for velocity, or we say proper velocity, we have eta alpha. Right. Now the free particle Lagrangian in terms of this eta alpha can be written as, well, first let's recall the relativistic free particle Lagrangian that we derived in the previous video, that was written or defined as L is equal to negative mc squared times the under root 1 minus v squared over c squared. Right, now this can also be written as negative mc over gamma times c. Right? Okay, so now also recall that we derived in one of our earlier videos that we said that eta alpha product eta alpha is defined as the constant c squared, right? And so then with this definition we can go ahead and write the Lagrangian as negative mc over gamma times the look, from here we have this c, right? And so we can write that c using this definition as under the root eta alpha, right? And so now we have this Lagrangian, and with this Lagrangian, then remember from your action that how your action integral could be written as we derived in the previous video. So with this definition of Lagrangian, now the action integral can be written as negative mc times the integral from some t1 to t2 of your eta alpha, right? And of course this integral is carried out over the proper time, right? Okay, so this invariant form can now be a starting point for the variational calculation that would lead us to the equation of motion. So you would do that obviously by using the principle of least action, right? So that states that the path that a particle would take is where the action will be minimum, and so using that definition on this action integral, you can then arrive at the equation of motion, that is d tau of eta alpha is equal to 0. Right. Now one can also further make the use of this constraint that we have. What is that? That is eta alpha is equal to c squared, right? Or the equivalent of this is also that we have eta alpha and the proper time derivative of eta alpha is equal to 0, right? But we also know that what our eta alpha is the proper time derivative of x alpha, right? That's then again it comes from the video where I derived for the proper velocity and proper time, right? Okay, and let's go to the next page And so now with these definitions, my this thing under the root eta alpha d tau can be expressed as the under the root of the proper time derivative of my x alpha. Alpha would come down, and again for this next one I'd have d tau x, and now this is a contravariant, so I'd have alpha in superscript, right? And we have, of course, we have this d tau, so let's write that d tau, which is outside the square root, right? Obviously. Okay, so well, the next step is pretty obvious. Let's bring down the indices. And how do we do that? We know we use the matrix tensor, and so then this whole thing above over here can be written as g alpha beta times the proper time derivative of x alpha and proper time derivative of x beta. Now it's in the subscript, right? And so let's make the square root a bit short, right? And of course we have this proper time differential, right? And now of course with this definition, what is this equal to? This is equal to under the root eta alpha d tau, right? Okay, so let's just put this in a box, and now let's see what does this equation tell us, or what does this equation mean, right? Well, it has the dimensions of displacement, right? And so if that's the case, then it is actually an infinitesimal length in a 4 space, right? Okay, so now note that we have this ds is defined or is equal to c d tau, right? Okay, so now with this substitution, what I can do is I can replace it in this equation, right? So let's actually go ahead and do that. Then this left hand side of this equation, what would that become, right? So let's go on the next page and let's write it down here. So that would then become under the root g alpha beta ds. Now the derivative is taken with respect to s, and s is my c times d tau, right? And note that this s is not the action, right? Okay, so it's the space-time separation. And so we have the derivative with respect to x of x alpha, and derivative with respect to s of my x beta. And so this would now be the differential element ds, right? Now note again that this s over here is not your action, right? But however, the action integral in terms of this infinitesimal length now takes the form that is s, which is now your action, is equal to negative mc times the integral from some initial space-time separation to some final space-time separation ds, and the term that you would have is then this thing over here. So what is that? That is square root g alpha beta derivative with respect to s of my x alpha times the derivative with respect to s of my x beta, right? And so now this is your this is the form of your action with in terms of the infinitesimal length, right? And so now here the 4 vector coordinate of the particle is actually your this thing that is x, it's your x alpha as a function of s, right? And this s over here is, again, it is the parameter which increases monotonically increasing with time, or proper time to be precise, right? Okay, now note that the action integral is along the whirl line of the particle, right? And so the principle of least action is the actual path, or the actual path, right? The if you remember, it is the geodesic, right? So it is the shortest path on the surface of a sphere. Now let's go to the next page and remember that from c d tau is equal to the square root of g alpha beta derivative with respect to s of my x alpha and derivative with respect to s of my x beta, right? And again over here my c is or is written as, or is equal to the square root of eta alpha times eta alpha, so this product, right? Now the next step is to find the equation of motion using the Euler-Lagrange equation, right? And so the if you remember now, the covariant Lagrangian, or the Lagrangian in covariant definition is, or we just defined it as negative MC square root G alpha beta ds x alpha times this ds, again it is the derivative with respect to s, right? And so derivative with respect to s of my x beta, right? So this is now the Lagrangian, where if you go back over here, over here, right? So this is how we define the Lagrangian, and then we worked out on this term that is in the square root, or the square root term. And so when we did that, we found that out to be equal to this term over here, right? That is in the box. And so then we defined our action, and so now with that term I just replaced that square root eta alpha times eta alpha, and so this is the Lagrangian that we get, right? So I hope you're following. And now we know the Euler-Lagrange equation would be derivative with respect to x alpha of our Lagrangian minus the proper time derivative of the, okay, so now what would we have here? We would have the partial derivative with respect to with respect to the derivative that is with respect to s of our x alpha of the Lagrange, right? So I hope you are getting this. What this thing over here means is, or actually let me just write it down for once over here. Okay, so this term that I underlined, what does this mean? That is nothing but the partial derivative, right, with respect to d derivative that is with respect to s of x alpha, and this derivative is for L, right? Okay, so that's what this term means. Now, okay, so let's go ahead and write the Euler-Lagrange equation that would then this be equal to 0. So we have over here we have the Lagrangian, right? And over here we have our Euler-Lagrange equation. So now the next step is that, as we said earlier, to write down the equations of motion. So from the Euler-Lagrange equation, now the first step would be to figure out what this quantity over here is, and if you look at the Lagrangian upstairs, that would simply be equal to 0, right? Okay, so that is equal to 0. Now let's look at the second term over here. And so for the second term, let's look at the term that is inside these brackets, right? So this term over here. So let's go ahead on the next page and compute that term. So we'll compute the term, let me write it down over here, we'll compute this term. So partial derivative with respect to the derivative with respect to x alpha of L, right, the Lagrangian. Right, so what is this equal to? Well, this would be equal to negative mc. Right, so remember that we have to take the derivative, right? So of the Lagrangian. So go back here and look at your Lagrangian, right? So we have this square root over the term that is that has this derivative with respect to s of our x alpha, right? And so taking the derivative of this whole term, we would get is negative mc over 2, right? And the term that is inside the square root, that is g alpha beta ds of x alpha, and derivative with respect to s of x beta power minus 1/2, right? We are just taking the derivative, right? And so the next term would be partial derivative with respect to derivative with respect to s of x alpha of this thing, and that is g alpha beta derivative with respect to s of x alpha derivative with respect to s of x beta. Right, so this second term over here, we are going to focus on this for now or for some time, and we are going to apply the product rule of derivatives, right? And so if we do that, let's see what do we get. So now I'm going to apply this product rule for this term over here, right, on this second term. And so what would that give me? That would be then equal to, that derivative would be equal to g alpha beta partial derivative with respect to s of x alpha of my ds, the derivative with respect to s of x alpha, times the derivative with respect to s of my x beta, plus, okay, so first we took the derivative with respect to derivative of this term, right, the first term, and now we would keep the first term as it is and we take the derivative of the next term, right? So that's the definition of the product rule. So what we would have is g alpha beta is going to be multiplied with derivative with respect to s of x alpha times the partial derivative of, or with respect to d, which is with respect to s of x alpha of ds, that is the derivative with respect to s of x beta, right? So let me just check this, right, and see if I did it correctly or if I made any mistake. Yeah, so it is like this, right? Okay, so now if you look at it, what we could see is that this in the first term, these two would cancel out, right? So what is that? That is your partial derivative of ds of x alpha with respect to ds x alpha. So that would cancel out and would go to 1, right? And so what we are left with is then g alpha beta d with respect to s of x beta plus g alpha beta derivative with respect to s of x alpha, and the last term, right? What would that be? That would be simply your delta function, that is delta alpha beta, right? So let's go ahead and get rid of this g alpha beta. So we would apply that, and what we would get is that your derivative with respect to s of x alpha plus the derivative with respect to s of x beta times your delta function alpha beta. Right. So now let's apply this delta function as well, and finally simplify this equation into we would get is derivative with respect to s of x alpha plus derivative with respect to s of x alpha, right? So all I have done is applied that Kronecker delta, and we got this thing, right? And so what is this? This is obviously equal to 2 times the derivative with respect to s of x alpha. Right, so remember that we were dealing with the second term so far, and now let's go ahead and the result that we got, we would substitute in this whole equation for this term, right? For this equation, right? So let's go ahead and do that. So what we would get is for this thing, right? Let me actually write it down. We would get for partial ds of x alpha of your Lagrangian, right? So for this term, what we would get is negative mc over 2 all of this over this thing, that is remember that this comes from your Lagrangian, right? So g alpha beta ds x alpha, which is again the derivative with respect to s of x alpha and derivative with respect to s of x beta, right? And this is multiplied by this term, that is 2 ds x alpha, right? And now if you look at it, this 2 and this 2 would go away, and what you would be left with is negative mc derivative with respect to, sorry, it looks funny, derivative with respect to s of x alpha, right, over this term over here in the square root. So g alpha beta ds x alpha ds x beta. Well, right. So with this now, remember what your Euler-Lagrange equation is, that is over here, and we figured out that this term vanishes, right, considering our Lagrangian, right? So we have figured out this second term, right, that is inside this proper time derivative, and now note that we have this negative sign over here, right? So this negative sign would go ahead and cancel out with this negative sign that we have over here, right? And so when we put this back into our Euler-Lagrange equation, what we would get is, so we would get a positive mc times the proper time derivative, right, of the derivative with respect to s of x alpha over this thing, that is square root g alpha beta derivative with respect to s of x alpha and derivative with respect to s of x. I'm sorry, that alpha would actually come downstairs, right? Okay, so then derivative with respect to s of x beta, and all of this is inside the square root. Right, so, and all of this is then equal to 0. This is what our Euler-Lagrange equation, that it takes this form now. So actually let me go ahead and put this in a box. Right, so using this equation, right, I'm also going to recall something that we already know, that is ds is simply equal to c times d tau, right? And so I'm going to use this definition for ds, and I'm going to substitute in this equation over here, and let's see what happens when we do that. So when we do that, what do we get? We get mc that we already have, right, and derivative with respect to proper time as it is, and now substituting, we would get 1 over c times d tau, right? 1 over c times d tau of x alpha, right? And now from here, if you go on, you'd see that your c and c goes away, and you're left with m derivative with respect to proper time tau. This actually doesn't look like tau. Yeah, and of course then the derivative with respect to again proper time tau of x alpha. And so this is just the derivative acting 2 times, so we can write it as the square, right? So finally, if you actually go back here and if you look at this equation, all this thing would be equal to 0 from this over here. And so what do we get? So let's neatly write it down. We get m times the proper time derivative squared, right, taken 2 times, of what? Of x alpha is equal to 0. Now if you look at this equation, this is your equation of motion, right? So this is your from Newton's second law, this is simply your ma, which is equal to 0, which is what you would expect, right, for a free particle. So this is the equation of motion for a free particle motion. And so our first, let me actually box this, right? Sorry. So our covariant description for the free particle Lagrangian is now complete, right? And so from here, the next wise step would be, of course, to look at such a particle that is bounded by some potential, or is let's say it is interacting, right? And so for that, we would have an interaction term in our original Lagrangian, that is for a free particle, and that would be only added to this Lagrangian, right? And so hence what we will do is in the next video, I'm going to look at the interaction Lagrangian, right? So that's it for this video. I hope you enjoyed and you understood this covariant treatment, and I hope you know the purpose for this covariant treatment of the Lagrangian. And this also goes and proves that our Lagrangian is actually Lorentz invariant, right? So yeah, that's it for this video. In the next video, hopefully we will talk about or we will include an interaction term in the Lagrangian as well.